I'll begin with a word of prayer as I get up here. So, Dearly Father, we thank you for this day. Again, I thank you for the students. I just ask that you'd bless our work today, help us to understand just a little bit more about matrix, multiplication, addition, all these things, and how to understand different ways we can look at a matrix, Lord. And we just thank you for your many blessings. In your name I pray, Lord Jesus. Amen. All right. So I introduced matrix multiplication last time. So if you missed that, you need to go back and write it out for yourself. It's important. I do expect you to know those things going forward. And so the main thing we learned is if you have A is m by n and B is n by p, then AB, if you calculate the ijth component of it, we can do so by the sum I equals 1, k equals 1 to n of aik bkj. So that's the definition of matrix multiplication. There are special cases like I talked about last class. But this we can calculate by row I of A dotted with column J of B, right? So that gets us the ijth component of the matrix AB. So that's one way we can look at matrix multiplication. And so let's do that. So suppose I have, let's say, 1 minus 1, 2, 0. And I'm multiplying by, let's say, 7, 8, 9, 10. All right? So to form this matrix multiplication, we can think about it in terms of like dot products, if you like. So this is really like 1 minus 1 dotted with 7, 8, 7, 9. And then 2, 0 dotted with 7, 9. Let's see here. 1 minus 1 dotted with 8, 10. And 2, 0 dotted with 8, 10. So I hope you guys know what a dot product is. Anybody not know what a dot product is? Okay, good. So the dot product we form, by multiplying the x times the x, the y times the y, and adding those together, right? The dot product of two vectors is a number. And so here, what do we got? This gives us what? 7 minus 9. Here we got 14 plus 0. Up here we got 8 minus 80. Down here we got 16 minus 0. So I put the dividers in just so you don't, when the numbers, I just put dividers in sometimes to help separate the numbers. They're not required, right? But if your reader is going to have trouble distinguishing which entry goes in which part of the matrix, it's helpful to put dividers in, right? But they're just window dressing, so to speak. Okay, so 7 minus 9 is, minus 2. Minus 72, 14, 16, right? So there you go. This 2 by 2 matrix times that 2 by 2 matrix gives me another 2 by 2 matrix, right? So this is an example of what's called a square matrix, right? A square matrix has the same number of rows and columns. So if this is A and this is B, we can also calculate BA. What do we get there? This time I won't write out all these steps. I'm just going to instead do it. So I have 7, 8 dot with 1, 2. That gives me 7 plus 16. Then I get 9 plus 2 times 10, which is 20. From the second column, I get minus 1 times 7, 8, which is the dot product with 7, 8, of course, is minus 7 plus 0, which is minus 7. And finally, I get minus 9. All right, times 10, times 0, plus 0, rather. So what is that? Well, that is equal to 23 minus 7, right? 29 minus 9. All right? And that's interesting, right? Because this is not equal to AB, right? See, this up here is AB. See that? So matrix multiplication, we have to be careful because the order in which we multiply the matrices matters, right? Matrix multiplication is not commutative. So if you say I'm multiplying by matrix, you have to clarify, are you multiplying on the left or on the right? Because in general, they're different, all right? They produce different outcomes. Any questions before I go on here? All right. So proposition. If you have A is an element of R m by n, and B is an element of R n by p, then we can write AB is A times, well, like B is the column 1 of B, column 2 of B, dot, 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 dot. How many columns are there in B? B is a what? What kind of matrix did we say it is? N by P. So how many columns are in B? P, right. So there's P columns in B. So listen, guys, there's about probably 4 different ways to look at matrix multiplication. The looking at it as a box of dot products is useful. This is yet another way to look at it. We'll see here in just a second here. So P. And so this is, so that's just notation so far, all right? Here's the actual content of the proposition, which is that this is equal to A times column 1 of B, A times column 2 of B, A times column P of B. So we can, this is the column by column multiplication rule. All right? So the proof of this, you know, I will spare you, but it's really just the definition of matrix multiplication and the definitions of columns. Rather than proving it, I'm going to illustrate it with my previous example. All right? So let's calculate some, let's look at example 1 from a different lens. So example 2, let us calculate A times V1 in the sense that I'm going to let A be the same matrix, 1 minus 1, 2, 0, and I'm going to let V1 be 7, 9. And then we're going to look at A V2, which I'm going to say same A, 1 minus 1, 2, 0, and then my vector is going to be 8, 10. All right, so how do we multiply a matrix times a column? So this is by, you know, essentially you just do 1 minus 1 dotted with 7, 9. That's the way that's calculated. And then you do 2, 0. dotted with 7, 9. That's the way so it's the same rule we just had over there. So of course these are the same numbers, which is 7 minus 9 and 2 times 4, 2 times 7. So we get minus 214 for that. And this one, I do 8 times 1 minus 10. And I do 2 times 8 plus 0 times 10. Right? So what's that work out to? How did I get an 80 over here, guys? You guys got to stop me, you know? You guys got to stop me when I do something wrong. See here, minus 2. Somebody in here knows that that's wrong. 16. Well, maybe not. You guys are all learning, right? So it's good for me to revisit an example 2 different ways because it might help me find the arithmetic mistake that I'm going to make because it's 8:15 in the morning. I need to make a formal request to not teach at this time. It's not good for you guys. So let's look back here at example 1 again. You guys tell me, what is nonsense here? Yeah, yeah. So I took the dot product in the 2, 2 spot, 1, 2 spot. I'll circle it. Right? This right here. That should give me 1 times 8 minus 1 times 10. Not this. Right? That should give me not 8 minus 80, but 8 minus 10. Which, of course, gives me negative 2. All right. So that's fixed. Now, once we make that modification, you see what's going on here? Minus 214. Oh, tell me I didn't make another mistake. Good night. Oh, the first one. I'm an idiot. I'm looking at BA, trying to compare it to AB. That would be dumb, wouldn't it? So what is V1 and V2 here? What did I do? They're column 1 and column 2 of my B matrix, right? So you see, we could do these 2 matrix column multiplications. 2 matrix column multiplications. So what I'm trying to say is that this proposition allows us to, basically take a matrix multiplication and look at it as a bunch of matrix column multiplications. See, because we put these 2 things together with the proposition, and we have A times the matrix V1, V2, allegedly is AV1, AV2, and indeed that's true because this is minus 214 minus 216. Did I do that right? Okay, good. And this, of course, is just B. And so this is, as I claimed, AB. All right. So there's that. Another thing that we should notice is that the matrix column product can be understood as follows. All right, so suppose I've got a matrix for A in R k by n and V in R n by 1. So that's to say that V is a column vector, all right? So we have A times V, right? So this can be understood as follows. This is V1, column 1 of A, plus V2, column 2 of A, plus dot, 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 plus V, how many components are there? Vn of them. Vn, column n of A. Let me put that into words. The matrix column product says that when we multiply a matrix times a column, what we're getting is a linear combination of the columns of the matrix with weights taken from the coefficients of the vector. This is a linear combination of columns of A with weights, or if you like, coefficients taken from V. Now, if we look back, right? If we look back at the matrix column products that I've already calculated today, we can see this in action. Like, let's look at, for example, AV1, right? My claim is that, so V1, see, that's unfortunate. This is something we're going to run up against, though. See, sometimes V1 is a component of the vector V, right? But you see what I did here? This, in example 2, V1 is a vector, right? So it's not the component of a vector, it's actually a vector. You're like, wait a minute, so you're telling me V1 can sometimes be a number and sometimes be a vector, and the context matters? Yes, I am saying that. I'm absolutely saying that. So you can't just judge something by the letter. You have to understand the context, and you have to explain your terms. So anyway, this is unfortunate. So I'm just going to have to illustrate by numbers, I suppose. So what I'm claiming is that this is 7 times column 1 of A plus 9 times column 2 of A, allegedly. So 7 times, what was column 1 of A? 1, 2. Plus 9 times column 2 of A, which was minus 1, 0. So what we got is we've got 7, 14 plus minus 9, 0, also known as minus 2, 14. See that? But totally different method of calculation, right? The way the numbers came together was really different, wasn't it? Yeah. But this interpretation is important. So let's look at another example. Example 4. If I have A is 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. All right. And I take A times the vector x, y, z. What happens here? So what that gives me is x times 1, 2, 3 plus y times 4, 5, 6 plus z times 7, 8, 9. So we can look at a matrix column product in this way. Now, in the textbook, which is technically required for this class, which I don't use too much this semester, we use my notes, right? But if you were to look in that textbook, you would find that it defines matrix multiplication first in terms of the matrix column product. And then later in the book, it uses the matrix column product to define the more general matrix multiplication. That's not the path we've gone down in here, but this actually essentially serves as the definition in the textbook. All right. Anyway, are we clear? So this is important, this idea that when we take a matrix times the column vector, we get a linear combination of columns. This is very important, like conceptually. And it's also a decent way to multiply matrices, but by default, I do this dot product, box of dot products thing, all right? So next up, I should talk to you about properties. And so here's some properties of matrix addition and Matrix multiplication. So this is theorem 2.3.17 in my notes. I probably could skip writing this on the board and everyone would be fine, but I'm going to write it just to emphasize what we know. And so what I'm writing down right now is simply the assertion that matrix multiplication, matrix scalar multiplication, and matrix addition, they all satisfy basically the expected rules of arithmetic. In other words, like you can distribute across the additions. Both the addition and the multiplication are what you'd say is associative. It doesn't matter which one you do first. We've already seen that it's not commutative, right? Like the matrix multiplication is not commutative. However, what I'm writing right now speaks to the fact that scalar multiplication is commutative. You can move scalars, numbers, to the left or to the right of matrix products and nothing is lost. Yeah?
On the second row of properties, what's that symbol between the A and Z?
X? That's just a big X, yeah. Big X. So, capital X if you like. But you could give it another name if you wanted.
But is it just a variable or does it mean something?
It's just a variable. So 1 times A is equal to A, and IM times A. Now that question you're asking becomes more interesting in what I'm currently writing. So X is literally just another variable name for us in here. Down here, there's a difference between what I'm writing. So this is like, let me number these things. 1, 2, 3, 4, 5, 6, 7, 8. Oh man, rats! I missed something because I'm to 8 in the notes here, but I'm on 7 here. Which one did I leave out? Doofus. Number 5. Oh yeah. My number 6. I'll fit it in here. Was supposed to be. Thank you. Very helpful. C1, C2. It would have taken me forever to find that in my current state, which is barely awake. Oh, yay, some banging. That always makes the classroom experience better. So C1, C2A, C1, C2. So that was 6. That's the 6 here. This is actually 7. I'm just trying to keep the numbering the same as the notes for the sake of reference, yeah? I don't expect you to refer to these by number or anything. It's just for the sake of a conversation here. Yep.
Where does the B come from on number 5?
Oh, that's a good question. The answer is the time slot or fall of man. Depends on how you want to look at it. But so that was a mistake. Thank you. And then finally 10. A times x plus y is ax plus ay. 11 a times c1x plus c2y is equal to c1ax plus c2. So all this is saying, guys, is that we can pull constants wherever we want. We can distribute across addition, right? And then finally 12 here, a plus b times x is equal to ax plus bx. All right. And now I need to add something here to the start of that. So so I'm missing some parentheses here, like this and that and this and that. Say it doesn't matter which one you multiply first or last, works out the same, right? So these are the rules of matrix algebra, right? The other rule was kind of provided to us by example 1, which is AB is not generally equal to BA. Really? So let me draw your attention to something here. So here, this is 1 in the reals, whereas this is IM is an M by M matrix. So definition, IM, the ij component of it, is equal to Kronecker delta ij, which is 1 if I is equal to j, and 0 if I is not equal to j. Right? This is called the identity matrix. So here I'm saying this is a M by M matrix. Right? So let me like prove some aspect of this here. So if I have IM times x, let x be in, let's say, Rm. So suppose x is an M vector. If I calculate the ith component of this, we learned last time that that's the sum over k equals 1 to m of the I sub m, the, let's see here, I k element of that times the kth element of x. That was our definition of matrix column product at the level of like summation notation last time. So here, because we defined this thing to be Kronecker delta, we have the sum k equals 1 to m of Kronecker delta ik, xk. Now the Kronecker delta is the natural enemy of the finite sum. It's almost always 0. It's only non-zero when what? When the indices are equal, right? So what happens here? You get 0 plus 0 plus 0 plus 0. What's the only non-zero thing here? I equals k, right? So this summation just drops down to x sub I. So what we have is that IM times x is, the ith component of it is just equal to xi, right? This holds for all I, right? For all I equals to what? 1, 2, m, right? It holds for all m components. So therefore, we get the following result. We get IM times the column vector is equal to the column vector again. IM times the column vector is equal to the column vector again. Similar calculations will show you that if I was to take a row vector, say v, times IM, I would get equal to v again. So any matrix appropriately sized times the identity matrix gives you back the matrix again. If I have that for a single column, I can get it, I can like prove this by just using the proposition in the middle board repeatedly on each column of the matrix A over and over again, right? Because I times the first column gives me the first column. I times the second column gives me the second column, and so forth, right? So if I know that, I can easily learn 9. So this identity matrix is important. It's like the number 1 for matrix multiplication, right? So the scalar multiplication by 1 is just what you expect. But this is something new. Can you guys tell me another way to look at the identity matrix? I'll just point this out. You can also look at it like this. IM is E1 concatenated with E2 concatenated with E. How many columns do I have? M at the moment. You can also look at the identity matrix as the standard basis that we talked about before, just glued together. All right, so let me prove something in here for you guys. So on our list of things to do here shortly, we'll probably next class look at how matrix column multiplication helps us to understand systems of linear equations in a new light in terms of like matrix column products. We'll do that. But at the moment, I should talk to you more about special kinds of matrices and maybe like a little bit about how we prove these properties, right? So this claim, for example, if we wanted to prove that A times B plus C was equal to AB plus AC, here's the way that goes. Actually, I think I did this last time. Let me not do that. I think I'm cycling back to last class. Let's see here. I don't want to hurry. I'm going to save a proof of one of those for next class. Instead, I'm going to give you a definition here. So definition. An element of Rn by n is, number one, symmetric if A transpose is equal to A again. Number two, it's antisymmetric if A transpose is actually equal to minus A. So this is a symmetric matrix and an antisymmetric matrix. So properties of the transpose that I should mention to you guys, right? What are some properties of the transpose? What are the properties of transposition? If we have, for example, A plus B transpose, it's A transpose plus B transpose. You had a constant. You can pull it out of transposition. All right. Those are the main ones. There's one other, I guess, kind of significant. What happens if you transpose transpose? What's A transpose transpose? You get back to A again, right? So, all right. So these are, the transpose map. So one thing we can notice is we can take any matrix, and we might be able to, see if it's symmetric or antisymmetric. Let's see here. So example, where am I? Example 5. So you guys tell me if I have A is equal to 1, 2, 3, 4, 5, 6, and then I put a 2, 3 here and a 5 here, what can you say about this matrix? Versus B is, let's say, 0, 2, minus 2, 0. So this is equal to A transpose, right? So the way transposition works, remember we define A transpose to flip the row to become a column. And so if you look at this, the first row is the first column, the second row is the second column, and the third row is the third column transposed, right? So A is a symmetric matrix. Another way to look at it is it has to be like, if you reflect the numbers across the diagonal, they have to match up. So this is a symmetric matrix, symmetric. And this over here is what? This is equal to minus B transpose, right? Because if I flip the diagonals, I get a minus there. So that's an antisymmetric matrix. All right. So the fact that we're zeros on the diagonal there, is that, yeah.
Is that always true if you look at diagonals, you can flip it?
Yeah, I mean, the definition of symmetric, the definition of transpose, rather, is this. A transpose ij is equal to AJI, right? So, like, for example, to prove property 1, if we did A plus B transpose the ijth component of that, it's equal to A plus B. ji, but how did we define a plus b, the jith component, remember? The jith component of a plus b is the jith component of a plus the jith component of b. Right? Which then is the ijth component of A transpose plus the ijth component of B transpose, right? So that's how these rules are proved. So since this is equal to that for all ij, it follows that that proves this property here, right? So to answer your question, I don't know, I'm not sure how to put that into, I'm not sure how to put that directly into index stuff. But yes, I mean, it's going to be the case that if, when you look at the matrix, if it's reflected exactly over the diagonal, I can see that geometrically. Don't make me write down an equation for that, but we can see it, right? Formally speaking, what you need is that row I of A transposed is equal to column I of A. That's the condition that you need for symmetric, right? Which is what I was just saying a second ago. If you take the column and you compare it to the row, they have to be the same, right? Just transposed, yep.
And for this, it requires a matrix that's the same size.
Yeah, we can only talk about a square matrix being symmetric or antisymmetric. All right, so one thing we can prove here while we're at it, how about this, my second example, we have zeros down the diagonal. Does that always happen for an antisymmetric matrix? Let's work on that. So here's a theorem. I keep thinking class ends at 9, and some of you guys start packing your bags up at like 8:55, which further adds to my delusion. So eventually I'll learn. Anyway, everything's fine. So, claim if A transpose equals to minus A, then the diagonal of A is 0. I mean, I guess I should say 0, 0, 0. I mean, if you think of the diagonal, you can think of it as a list of things. I mean, more to the point, I is equal to 0, for all I. So the proof is very simple. Here's how it goes. If A transpose is equal to minus A, then A transpose II is equal to minus A II, right? But what's the definition of transpose? It does what? It flips the indices, right? It changes II to, well, it's kind of embarrassing, II, right? So it's kind of dumb. So like the swapping of indices, when you have them both equal, it's kind of hard to, but so A transpose II is, well, A transpose II, excuse me, AII rather. AII. And this is minus AII, which tells me what? Twice AII is equal to 0. Therefore, AII is equal to 0. So an antisymmetric matrix has to have zeros down the diagonal. Symmetric matrix doesn't have to have zeros down the diagonal. Whatever, right? So that's one thing. Let's see here, example 6. Let's see here. Another important kind of matrix product we should look at for a second here. What if I have, let me make the matrix specific here. What if I have like we'll put 1, 2, 3 in the first column, all right, and then 4, 5, 6 in the second column, like that, all right? And let's multiply that by 1, 0. See what we get. And let's take that same matrix, 1, 2, 3, 4, 5, 6, and multiply by 0, 1. And then let's also take that same matrix and multiply it by 1, 0, 0 as a row vector. And let's take that and multiply it by 0, 1, 0. And let's multiply it by 0, 0, 1. And let's see what happens in all these cases. So what happens is when we multiply by 1, 0, we get 1, 2, 3. When I multiply by 0, 1, I get 0, 0 plus 4, 0 plus 5, 0 plus 6. I get 4, 5, 6. This is not an accident. Generally speaking, what happens is if you take a matrix A times the ith standard basis element, you get column I of A. This is actually a general rule of matrix multiplication. If you want to select the ith column of a matrix, simply multiply by the vector which has a 1 in the ith component and 0 is elsewhere. That's what that does. How about over here? This gives me 1, 4. This gives me 2, 5. This gives me 3, 6. This is not an accident. If you take I transpose and multiply it by A, you get rho I of A. This is not an accident. This is a general result. If you want to select the ith row of a matrix, you can multiply on the left by the transpose of the ith standard basis, and it will select for you the ith row of the matrix. These are important observations. We will use these over and over again in simplifying various matrix calculations. So you need to just Selah. Excuse me, Selah. Which means what? We don't really know, but oftentimes people say pause and calmly think of this. So that's all I'm saying there. But anyway, so we're pretty much done for today. Sorry I got started a minute late because of, stuff. But anyway, I'll see you guys Friday, I hope. Thanks, everybody.